Deeparnab Chakrabarty from Dartmouth. Professor Deeparnab did his PhD from Georgia Tech and followed it up with postdocs at University of Waterloo and University of Pennsylvania. And following a 5-year research stint at Microsoft Research Bangalore, right here, he joined as a faculty at Dartmouth College. His research interests lie in the intersection of algorithms, and today he will be talking to us on the topic round-occur technique for clustering problems. So, further ado, I hand it over to you.
Thank you for the introduction. So it's great to be back at IISc. As mentioned, I was at Microsoft Research for 5 years, and while I was there, I actually taught 2 courses here on approximation algorithm. Co-taught actually, Dartmouth, Acharya, and that really rekindled this, or not rekindled, it sort of led me to realize that I like teaching and led me to this academic path. So I'm really grateful for IISc having this option to talk again. I'm also on the path from my place in Bombay to my in-laws place in Chennai, and back in Arindam was really grateful to organize and invite me here. So thank you for doing that. My apology is that I'm going to give a technical talk, right? So the talk will be on technique and approximation algorithms for clustering problems. So I'll be talking mostly about algorithmic techniques rather than problems themselves, or why. So I'll not motivate much, etc. And my hope is that there will be something at least that everyone will take away from this talk. So we have already some parts of them some experts might know, and some parts people who are not doing approximation algorithms. Okay, so let me begin. So since it's going to be a technical talk, it's good to start off with the last slide. So I'm going to start off with this slide that these are the take-home points that for clustering problems, sometimes using tools from mathematical optimizer, linear programming gives you better algorithms, or in particular approximation algorithms. And the second thing that I want to take away is that there's an idea called the round-occur paradigm, which has been useful in various problems, various clustering problems as well, but it's still not made it into textbooks. That's something that I want to sort of, again, this will be the half of the talk. I'm going to talk about one clustering problem. So there are gazillions of clustering problems. I'm going to take one clustering objective. As I said, I will be sticking on problems, not too many problems, and look at two generalizations, respective generalizations. And we'll see 3 sophisticated, increasing order of sophistication algorithms for them. The first one will not require any linear programming. The second one will, and the third one will introduce this counter. Okay, so let me tell you what the problem. So the problem that I'm going to talk about is called the K-center problem. So we are given some points in a metric space, and I'm going to call these points clients. Okay, and will be denoted with blue circles. And we also have some other points which are the squares, which I'm going to call facilities. So these are the points which are going to be sort of the candidate sectors. That's the input. These points live in a metric space, so they satisfy tangent inequality. That's the only thing I'll assume. So it's distance between A to B is at most distance between A to C plus distance C. That's the only thing I'll assume. And I'm also given this number here. What's the objective? Objective is to figure out K centers. So I want to figure out K of these facilities. I want to open them. And once I open these facilities, every client travels to their nearest open center. And the distance a client pays is that distance that they travel. So that's this dV of S. Now every client therefore has a number on its head, right? That's the distance that they've paid. And now you can say, okay, there can be a function of these these various numbers. I want to sort of maximize or minimize or optimize this function. So the K-center objective is basically going to try to minimize the maximum. So I open K-centers. Everybody travels a certain distance. I have a bunch of numbers. There's the largest among them. I want to minimize that. That's the problem. Is the problem clear? Also, I should basically mention to please ask questions. Okay, so anytime there's a question, just raise your hand and ask it. I not only encourage it, I recommend it. So that's the problem. So of course, there are many different ways of choosing an NP-hard problem. So another way of stating the same problem is I'm given these blue points in the metric space. Find the smallest radius R so that k balls of radius r can cover all these blue points with a constraint that the centers of these balls must be on these squares. So that's this underlying point. So that's the same thing because if that's the r, which will be the maximum distance. So that's a geometric viewpoint of this. The reason I've underlined that is I might even ask this. One could ask this, and people have asked this problem without restriction on where the center could be, and that will be a different problem. For today, this is the problem. The centers of these places are even open with balls. Okay, so that's the k-center problem. Good, thank you. So this is for the star. The asterisk is for the experts. So the experts might say, this is not the k-center problem, but it's called the k-supplier problem. The k-center problem is actually the special case when f, the set of squares, is equal to the set of circles. So f is equal to c. But let's just forget that. Okay, so this is the problem. I'm going to call this the k-center problem. Okay, thanks. So this problem has been studied for a lot of many years. So the earliest thing that I could find which actually stated this problem is this paper from the 70s. But this problem is NP hard. Okay, so you cannot find an efficient algorithm which finds this R exactly. And in fact, you cannot even get a 2.9999 approximation algorithm. So if there's an algorithm which approximates this radius R to this 2.99 factor, then there is actually an algorithm which solves it exactly, and therefore P is equal to NP. So we don't expect such things to happen. On the other hand, there are many efficient and fast 3 approximation algorithms. So the algorithm will take this instance and will find a solution where the radius that will be outputted is guaranteed to be within at most 3 times the test radius. So that's the definition of approximation. Okay, I write this in bold because we're going to look at this algorithm. This is going to be our first algorithm. It will be completely combinatorial, no linear programs will be solved, and then we look at the general. Okay.
These are like for arbitrary. It's a special matrix I think they are better.
Yes, so I'm going to be talking about completely nothing more will be assumed other than the triangular inequality. But even and you can ask this. Okay, suppose the metric space is actually the Euclidean metric space on a plane. So even there, that's actually a problem since you mentioned it. It's still open. The answer is some number. There's a gap between two numbers. So that's hardness. But we are going to be talking about general. So one technicality before I move on. So we're going to look at. So we're going to always assume that we know the optimal radius value. So I'm going to guess. So there is this R star. We're going to try to guess that. So we're going to guess a value R, and we're going to actually just solve this yellow box problem. So given that R, we're either going to find a solution every point within distance 3R. Okay, so we're going to find k center so that every blue point is within 3R of an open square. Or we are going to prove, that's step B, that the guess R that we have made is too small. We're going to certify that the optimal answer is going to be strictly bigger than R. Okay? So this is actually the only thing that we'll solve. So if you can solve this, then it's not too hard to see. And if you don't see it, don't worry about it. That if you can put this on you can put an outer wrapper of binary search on this R to get a 3 also. So henceforth, that's all we're going to do. We're going to assume that there's an R given to us, and our goal is either to say, is this R too small that the true optimum is actually bigger than R, or find me a solution to within distance 3. This is a technical side. This is the problem we're going to solve, part A or part B. Okay, so with that in mind, let's look at an algorithm for the k-center problem. Like as I said, there are many algorithms. So this is going to be one algorithm, which I'm going to call the Hochbaum-Schmalz algorithm from the 80s. So here is what it does. So the first step, it picks an arbitrary client. Okay, picks an arbitrary blue point, and it calls it a representative. I'm going to put that blue point in the representative set. Now it opens a facility in at a ball of radius R around this client. So why do I know such a facility exists? Well, if there is no such facility, then I'm in part B. R star is bigger, smaller than R, so I'll be in part B. And it just opens it. So that's one open center. Then it draws a ball of radius 2R around that same representative. And whoever clients are in that ball, whichever the blue clients in that yellowish, orangish ball there, they are called the children of this representative. So this representative is going to take care of these points. Then it deletes all these children and the point itself from the set of clients and just repeats. Okay, so the next point might be that point there. It draws a ball of radius r, opens a facility, also draws a ball of radius 2r, says that all these clients are my children, deletes them, and keeps on till the set of clients become empty. That's the algorithm. So there are two things to be said here. One, claim one is that every client is going to be within 3R from one of the open facilities. The second thing is that I open only K clients. That's the first part. Every client is within distance 3R from some open center. And this thing that I'm going to say next is going to be the reason for every other, not every other, two other things that we'll be talking about. Okay, so why is that the case? So pick a client like this here, that client to the right. Now that client has been removed at some point with the children of some representative. So let's go consider the representative there. It is within distance 2R from the representative. And the representative has opened a facility within distance R from itself. So by triangle inequality, that client is removed. This is 3R from 1. That's the 3 that is going to be there. Clear? Good. So what is not very clear is why have I not opened many more clients, many more facilities? Why have I stopped at only K? Because the algorithm claim is that at most K centers are open, but actually it's not quite true. If I open more than K centers, then my radius case is too small. That's actually the correct thing to say. So why is that the case? So the key observation, and this observation is good to keep in mind, is that the representatives are far away by design. Right? So any two representatives are within distance 2R away. Why? Otherwise, the first representative would have eaten up with the second. Which means that these yellow balls are disjoint. Okay, so these yellow balls are disjoint. Now, suppose I opened more than K centers. Suppose I opened K plus 1 centers. What does that mean? It means that there are K plus 1 disjoint yellow balls. But that means that any solution which covers these K plus 1 points must, if you open fewer than K plus 1 things, you must be traveling more than distance R. Which is basically if you open more than K plus 1 centers, or if you have more than K plus 1 yellow balls, disjoint yellow balls, then the optimum guess is bigger than R. R is too small, I guess, going back and forth. Is that clear? So the thing is that if I open more than K, so the key thing to remember, which will come back again, is that these yellow balls are all disjoint by design. Okay. And that's it. So we've solved that yellow box problem, and this leads with the outer wrapper to an efficient 3 approximation. Questions?
Is the right case for this?
Yes. So the problem is NP hard. So the problem it is NP hard to approximate to any factor better than 3. So not only this algorithm, any algorithm potentially has tight instance, but in particular for this one, it is not too hard to construct a tight instance. So it is as bad as it. Was that the question for this particular algorithm? Are there instances? The answer is yes. Other questions?
You use an upper bound for R as a whole bounding box and then do binary search. But the facilities can be spread out a lot, right? Why not do a guess and double instead of that binary search? Is that significant thing to this?
The guess and double of the binary search is almost the same idea. As in, you could start with the bigger, or you could start with smaller and then keep doubling, and at some point come back down. That would also work.
Can you not construct a bad example where the binary search would take you really spread the point out?
Yes.
You did not do strictly do worse than.
So actually, if you think about it, the optimum thing, there are only n square possibilities, because it's going to be one of these distances between square and a circle. So you could, so it will be log n of n square at most. To binary representation. Good. Other questions?
It's interpreted somehow as like a coverage. It has that flavor, right? Like you're doing this. It's not really submodular. The coverage is built has it, but I kind of see the. I mean, it has this idea that you pick another one with a bigger thing in it, but you're not even accounting for it. See, pick an arbitrary one now.
Yeah, right. So there are two things that I hear from you. So one is, second thing is that you said is that arbitrary seems like arbitrary. There's nothing really or something going on. Put a pin on that. The other one, that connection to coverage, you could think of it as a coverage problem, but a coverage problem does not allow or has no notion of a dilation. A set covers these elements, but there is no notion of a dilation. So this, because we are in a metric space, has even a notion. That's why this is a spoken code. You can ask this question. That's a good proof. Fantastic. Other, yes.
Is it obvious that any covering of radius 3r will come from this algorithm by picking choice of order of fields? You have case-centric covering.
So let me ask you a question again to see if I understood it. Any three approximation algorithm, can you think of it as this algorithm where the order is a certain order? Is that no?
3r centric covering is there.
Yeah.
So some covering is there which covers the whole of. Will it can we choose the order of arbitrary fields which can make that covering?
I understand your question. My first guess would be probably not, because I can think of a 3R solution where every point in a cluster is 3R away from a center. But here, one of the points is always going to be within R distance. The representative is always within R distance from the center. So it's not possibly I can come up with an instance where what you are saying is probably. Okay. Are we ready for a generalization? Okay, great. So what is, sort of to motivate this generalization, let me sort of say what is one issue with this objective itself, this case center objective, and the issue is that it is highly sensitive to outliers. So consider the same data set that was there as in the previous example, but there's one other blue circle which is very far away. I want to solve the case center, suppose I use the case center objective for even for K3. Well, no matter what you pick, the answer will be basically that, since I'm looking at the max, that is going to lead to a large objective. I'm not going to get a value. So why are we solving this clustering problem? We're probably trying to solve it to get the cluster. Maybe the objective is just a means to an end, and that outlier will completely screw us. Right? So that's why this is an issue with this case center objective. And to overcome this, people looked at this problem called the case centers with outliers, the robust case center problem, which is the input is again the same things as for the case center, but there's an extra quantity m. Okay, so there's a natural number m. M is between 1 and the number of blue points, number of points. And this is supposed to be the coverage of the number of inliers, number of points that you need to cover. And what's the objective now? The output is not only do you have to figure out the centers to open, you also have to figure out the clients to cover. You want to find a set S to open, and you want to find a subset T of clients which you want to cover, and this set of size T should be at least M. So I'm covering M clients, and then our things that are not in T, I just throw them away, and all I want to minimize is the maximum distance a client in T travels to an open set. So in this case, for example, there are 1, 2, 3, 4, 5, 4, 9. N is equal to 10, but if M is equal to 9, then the solution would be this. Okay. So if you have such an algorithm, maybe you can tweak M and you can find at a certain level, certain clustering. So this problem is an important problem. Clearly, it's a generalization, because if M was equal to the number of clients, then it would be the case center problem. If I had to cover, if M was equal to N, I had to cover every client. I'll get back the case center. So this is a generalization. So what is known? So it's as hard as 3. You're going to do better than 3 approximation for this.
It is set cover to max coverage.
It is set cover to max coverage, except set cover is a dual problem of minimizing this. Excellent. So what is known? Well, there is also an efficient approximation algorithm, and the bold means that you're going to see it. But if you remember Hopbaum-Schmoiger from the 80s, and this was much later, like there's a paper by Charikar, Fuller, Mount, and Narasimhan, and it's a really, really clever, greedy algorithm. So no LPs are needed to get this approximation. Greedy algorithm, and there the order in which you open is something like this. But I'm not going to talk about that algorithm. Instead, I'm going to sort of tell you, to me at least, so this algorithm is a very clever algorithm. I'm not a bad fan of cleverness. I'm going to show what I feel is a very generic algorithm, but uses linear programming. So it's not going to be, maybe it will be as fast as this one, we don't know. But that's one algorithm that actually came out when I was at Microsoft. And Prachi Goel was actually a student here doing MSR fellowship. And Ravi Shankar Krishnaswamy is my colleague. So this is a paper. Of course, the catch is that the thing that I want to tell you, you'll not find in this paper. So it sort of arises from there. And I'll bring back that star which has vanished from here. So this Charikar et al. Paper is actually a 3 approximation even for the robust case center problem where the squares and the circles are the same set. But what we could do is get a 2 approximation. So there is something, so the LPs do have certain power. So the combinatorial, we don't know if there's a single 2 approximation. But forget that if that didn't make sense. Let's come back to this. We're going to look at this algorithm. I'm going to use this to describe this as a linear programming. Okay, again, so that's the instance. So what does the linear programming idea do? It's basically cast this as an optimization problem, a continuous optimization problem. So we're going to have variables. So there will be a variable xf for every square, which indicates whether I open the center or not. Okay, so 0 means not open, 1 means open, but I cannot keep it at 0, 1. So I'm going to have this xf go between 0 and 1 continuously. So I'm going to have that variable. Now I'm going to have this coverage variable for every vertex, which basically says, is this vertex V going to be in my final set T or not? Whether I'm going to cover it or not at all. And that is also going to be between 0 and 1. Okay, so these are my variables, and it sort of makes sense what they do. What are the constraints? Well, 2 constraints are sort of maybe simple. One is that you cannot open more than k centers. So in fact, exactly k centers are open. So that's summation xf is equal to k. And the second constraint is that I have to cover at least m clients. So the summation of the coverages is at least m. So once again, I want to cover m clients. So if cubs were 0 or 1, there will be m things with 1 on their heads and 0 things, everyone else will have 0. But since I'm allowing it to smear, cubs will could potentially have every client would have a cub on their head, but maybe they are fractional. The only thing is that the total sum of these fractions would be at least. So that's a constraint. And the third constraint is what connects these x's and dots. Okay? And it connects in the natural way. It basically says, if I take a client there which has some coverage, well, where is this coverage coming from? Its coverage is coming from because I've opened a facility within distance r from it. So if I look at a ball of radius r around that vertex V, and I look at all the facilities that are in there, one of them must be open. So if cub V is 1, one of these must be 1. I don't know which one. So I'm going to add up all the x in this yellow ball. So that's that summation there. Summation of xf over all f's in this yellow ball. And that summation should be at least the coverage. If you don't open, so what is in English? If you don't open enough facilities in my neighborhood, you cannot hope to cover. So that's that. Okay, so again, if you're seeing this for the first time, it sort of feels, what is going on. But it's basically in English, it says, if you're covering me, you must be paying for or doing so because you opened somebody right now. Okay, so this is a system of linear inequalities. Okay, I can write them. And here is the thing to remember that. So again, the R is a guess, right? That R in the denominator, the ball of radius R is a guess. So if the system of linear inequalities does not have a feasible solution, I can fit it to a solver and it has no solution, then my guess is too small. Then I'm in part B of my yellow box. But if it has a solution, now we are going to give a solution, a true solution, which is where every open facility, not every open facility, at least m clients are within distance. Okay, so let's look at that algorithm. You got any questions about this LP? Yes. The solution will be non-NP. I cannot hope, it will be a very nice accident for me if the solution is integral, in which case, wherever I have xf equal to 1, I'll open those facilities and I'm done. But I am worried that the solution will be non-integral. So in fact, if you think of the solutions to be like smear fractions all over. So that's the thing to keep in mind. So with that, we're going to look at a rounding algorithm. We're going to go from a fractional solution, we're going to round it to an integer solution. That's the round part of the round of that. And here is how it goes. It's very similar. The skeleton will be very similar for the Hofbauer-Schmois. I'll actually note down the changes. So Hofbauer-Schmois pick an arbitrary V. Now I'm going to pick a V with the largest curve. Okay. Again, it makes sense. If somebody has not been covered by the LP, if some LPS coverage is 0, then it's an outlier. I should kick it out. So this is just a greedy version of this. I pick the client with the largest coverage, and that's fractional. Maybe it's 0.97. So I draw a ball of radius r around it. And now, instead of opening a facility within distance r, I just tentatively select it. Again, this is important. I select it. I don't open it. I select it. So that's that. I draw a ball of radius 2r, and whichever clients are there, they are my children. I remove them, and I keep repeating this. So that's the first step. Then maybe I do this. I draw a ball of radius, that went away, then I do that went away. No, I'm not resolving yet. So I've solved the LP, I'm using this, and I'm just creating this. Okay. So at the end of this, what has happened, I have selected some representatives, and I've selected some facilities, but I've not opened any of them. And in this example, think of K as 2, and we've actually selected 3. We've selected more than our budget. And in fact, if you see that, there might be some facilities which have no clients, there might be some clients which have no facilities in the yellow ball. What does that mean? It means that coverage must be 0 because there is no facility around it. That's fine, we'll take them as well. Okay? So the algorithm is not over. So each representative B has some number of children which are in their balls. So I'm going to take that number and put that on their heads. So every representative has a number on their head, which indicates the number of children, number of clients in their orange ball. And now I'm just going to open K of the largest number. So there are a bunch of numbers here. So K is 2 in this example. So 5, 2, 2, 1. 5 and 2 are the largest. I could have chosen that 2 as well. And I open the respective selected facilities. And whoever these children are, that's my set T. I cover these things. That's the algorithm. The algorithm clear?
The interesting part is you have to show that M gets.
Excellent, right? So let's, So that's the interesting part. One thing I would like you to keep in mind that although the LP had XF variables, we did not use them in this. We only use the coverages. And this will be important for the next half. Okay. So why is this, what is the analysis? So first of all, every covered client is within distance 3R from an open center. The same reason as before. Every covered client is covered because it's in the orange ball of someone whose yellow ball has an open facility. So that's the same. And at most K centers opened, well, that's by design. But as it pointed out, the non-trivial part, not at all clear part, is why have I covered at least M clients, right? So let's go over this. This is a bit of math here, but chain of inequality, not really math. So what do I know about M? So what is the LP set? The LP set, even if you smear these fractions on every client, the total mass, the total sum of smeared fractions is at least M. That is what I know. And now what can I say about this sum on the right? Well, I can sort of partition them. I can go, this summation is over all clients. So I can say, go over all representatives, go over the children of the representatives, and sum of their coverages. And now I'm going to use the fact that I chose greedily, which means that any representative's coverage is at least their children's coverage. So I can replace that cov u equality. So I'm going to say cov u, when u is a child of v, is at most cov v. And so I get that cov v times number of children summed over all the representatives. This sum is at least. Okay. So this is the part where I've used the design of the algorithm. So this is so the cov u's on the second inequality, they are all at most cov v if u is a child of v. So how many children does v have? And that's precisely the number of children. So again, in this example, what I get is that if A, B, P, and Q are the representatives, then 5 times curve of A plus 2 times curve of B plus 2 times curve of P plus 1 times curve of Q is at least M. It's an inequality that I've gotten. I've opened A plus B, so I need to show that 5 plus 2 is at least M. That is not clear yet. But what is going to make this clear is looking at this sum. So the representatives, if I look at just their coverages, not everybody else's coverages, just the representatives' coverages, my claim is that this number is small. How small? Well, let's look at what curve of A is. So what is curve of A? Well, curve of A is at most the total X mass in the yellow ball around A. Because that's what the LP said, right? A gets covered if somebody in a distance of radius R has been opened. So that's what says that the curve of A is at most the X mass of the yellow ball around A. Is that clear? I'm not writing inequalities anymore. This is sort of very colloquially I'm saying that. X mass is the sum of the X of all the squares in that yellow ball. Similarly, curve of B is the total. If I look at the ball of radius R around B and I sum the X's in those squares, that's curve of B. Curve of P is at most this. Curve of Q is at most this. So what does that mean? It means that if I sum the coverages of the representatives, that is at most the X mass of the A ball plus X mass of the B ball plus X mass of the Q ball plus X mass of the P ball. But these balls, if you remember, are disjoint. So if I sum up these X masses, no double counting is happening. So that sum of the balls is at most the total X sum overall. That's what is written there. But how much is the total X mass overall? At most K, because that's another constraint in the LP. I'm not allowed to open more than K. So this is at most. So now I have two inequalities. Okay. And what is the algorithm doing? It's picking the K largest from the top. Well, it's just a simple inductive proof that if you have an inequality and linear representation on the top, linear combination on the top, which sum is at most K, and if you pick the K largest thing, the coefficients must be at least that. K is equal to 1, it's just saying that the max is at least the average, and after that you can proceed inductive. So therefore, in this example, if we take 5 plus 2, that number 7 is at least M. So what have we done? So this part, so I'll just say it again. On the top, I have a linear combination of these coefficients, 5, 2, 2, 1 being at least M. And the things that are multiplying these things, they sum up to at most K. So if K was 1, this will be a distribution which is at least M, so the largest is at least M. And if it's not, but it does not really matter, if you have K equal to 2, then the largest is at least M minus that, and then you can proceed in that. So this is a fact that it's just arithmetic at this point. And therefore, I covered at least M clients, and that leads to this theorem. Okay, so we needed to solve an LP. Questions?
Don't have any objective.
No, we don't have any objective. So the objective is actually this R thing that I'm trying to minimize. So instead of minimizing R, because then I cannot do that because R is going in the constraint, I guess the R because there's only one single scalar. And once I guess the R, I can actually fit it in the constraint. So it's just checking the feasibility of a system of inequalities. If it is infeasible, my guess is too small. If it is feasible, I get something within distance 3R. So that's that we are.
You are having a constraint of the number of it is in the integral solution, the number of facilities open is exactly as opposed to previous algorithm where you could open less. So say if an instance is not a tight instance, will this help you perform that?
So I could have had at most K because opening more facilities can only help us. But your question is, can this LP do better?
If the instance is not tight.
If the instance is not?
It's not the robust variant in the previous question. If the instance is not tight, can it?
Again, worst case, no. The worst case, it won't really There are instances where the LP will be feasible, the R, but you will still need 3R to cover everything. You will not be able to do it very well. But in an arbitrary instance that you want to solve, it could be that the LP is doing better thing than a, because it is, the algorithm is after all doing something, it's not giving an arbitrary view. Yeah. So maybe if you had, if someone put a gun on your head to solve the case center, maybe solving the LP would not be a bad idea, but the other algorithm might also be good. Other questions? Yeah. Reverse may not be true. Yes. Yes. But even then, I am within distance 3R. So it could be that R is less than R star, but I am finding a solution within at most 3R, which is clearly at most 3R star in this case. That might not have a facility inside, as was the case for this study. But in that case, the coverage must be 0, because there is a constraint which says the coverage of this client is at most the X mass of the facilities in that yellow ball. So if there is no facility, that is 0, so curve will be 0. The LP has that sanity check. Good. Other questions?
Counting aspect is used critically. Like the weighted. It's a very mechanical question.
No, ask it because you might segue me to the next thing.
Okay, but yeah, like the weighted thing is also interesting. Weights with.
Yeah. That is the next problem generalization. So yes. Okay. So this is half time in some notion of, it's a constant approximation to a half time. So let me move on. I know I'm between you and lunch. So this is the thing that Sid mentioned. So we're going to look at a generalization of the robust case center where not all centers are equal. So right now we're saying you open case centers, every center is $1 to open, so you just open case centers. But now in this knapsack center version, the problem is slightly different. Instead of a K being a number, natural number, it's some rational number. And now every facility, every of these squares has its own weight. So think of this as a number of money required to open a facility there, and this may not be uniform from facility to facility. So there is a weight on every facility. And the objective again is to find a set of centers S, whose cardinality is not at most K, but the total weight is at most K. Total money required to open this is at most K. K is this budget. And again, the robustness version is still there. I need to find a subset of clients whose total number is at least 10, that should be at least 10, and I want to minimize the maximum distance. So this is a generalization. And you can think of the generalization already without the robustness. I want to find centers whose total weight, total budget to open this is at most K, but everybody needs to be covered. You can think of that. It's an exercise, if you've, that, not completely easy, but it's a nice exercise to see if you've understood the case center algorithm, to see that there is a way in which you can choose this ordering so that you get a 3 approximation for the non-robust version. But we are going to look at this robust version. Is the problem clear? The only difference between this and the previous is that I have weights on every facility, and the total weight that I am allowed, the total budget is at most. So it's a knapsack-like thing. We're going to talk about, there's an efficient 3 approximation for this as well. That's going to be, the generalization. So this is the best possible. And this is a result with my student Mariam. And this will actually show the new technique. So finally come to the new technique. So let's straight away, and in fact, maybe I actually don't know of a combinatorial algorithm for this. So again, for the robust case center, as I said, there was a Charikar et al. Paper, which is a combinatorial, is a fast, greedy type, very clever algorithm to get a 3 approximation. For this one, I don't know. In fact, for this one, I don't know for even a quote-unquote fast algorithm. The running time of this algorithm is not clear. The previous one, the linear, the LP is so nice that you can actually solve it pretty fast. Yeah.
You don't know of a combinatorial approximation or just any combination?
Actually, I don't know if a combinatorial any approximation. Any, by any way, I mean any approximation.
You tried like the knapsack along with the approximation.
So what I know is there is an approximation. If you violate the M by a little bit, then you can get it. But if you want to serve at least M clients and not 0.99 M clients, then I actually don't know.
No, the approximation will be on the gates.
Correct. Yeah. So short answer is I don't know. In fact, the p-test will be used. Anyway, so what is so I would at least like to get to the place where to show you that what fails. We can write a very similar LP as before. With the only difference is that instead of summation xf at most k, which was saying I open at most k facilities, now I say that I open at most the total weight of facilities open is at most. That summation w of xf is at most. And if you've seen knapsack, you can sort of already guess that I'm in for trouble. Okay? But I would like to show you this trouble. Okay, again, right? So this is so I'm now going to say that this LP has a bad integrality gap. This LP can cheat. What do I mean by that? So we can show an example, and this is an example. I'll go through it a little bit. Such that for a certain value of R, the LP has a feasible solution. Okay? Again, if the LP does not have a feasible solution, R, my guess is too small. I can double my radius. But for a certain small R, the LP has a feasible solution, but there is no integral solution. It's like 3R, 10R. There is no finite integral solution. And this is the example. I have two facilities, A and B. There are 6 clients around them. The weight of client facility A is that same number 6, while the weight of facility B is 1. My budget is 6, and I have to cover 11 of these 12. Now, obviously, you cannot cover more than 6 clients. You have a budget of 6, you can open only 1 facility. So you can cover at most 6 clients, right? But the LP can cheat. The LP can cheat by saying, I'm actually not going to open that facility A up to the full extent, but only to a small extent. So let me say what I mean. So this is the LP solution to the previous LP, which says put 5/6 mass on A and 1 mass on B. So B is fully open, but A is only 5/6 open. And since I've opened only 5/6, every client in around A has also coverage 5/6. It cannot get anything more. But the total sum of coverages for these 6 fellows with 5/6 on them is 5, and these coverages around B gives me 6. So M is equal to 1. So the LP has a feasible solution, but again, you cannot integrally you cannot do anything. Okay, so this is an example of integrality. Okay, so this happens often in approximation algorithms. You want to solve the problem, you write a natural LP that comes to mind, and you find an integrality gap, and what do you do next? So the round or cut technique, the generic technique, is one way out of many ways to sort of navigate this thing, right? So I want to sort of, so this is in some sense the slide that captures the essence of this round or cut. We already had a rounding algorithm for a simpler version, right? When the weights were all 1, we had a rounding algorithm. We just saw. Let's see what happens when I apply it. So what will happen? So I'm going to. So why doesn't the previous algorithm work? It cannot work. So what happens? So it picks the client with the largest coverage. Maybe it picks that as a representative. It selects that B. It draws a ball of radius 2R, and it covers everyone. Like it not covers. They are the children. And then it picks this and does that. So these are the 2 representatives. And what do I get? Well, if you go over the same inequality that we wrote, the 5 curve A plus 2 curve, something similar you will get here. You'll get that 6 curve P, 6 being that number, plus 6 curve Q is at least 11. That part is fine. But the previous one, we had curve A plus curve B, is at most K. We cannot have that anymore because there are weights involved. So what you will have is actually, you look at every representative, look at the ball of radius R, look at the facility with the minimum weight, that times curve, if you sum them up, will be at most K. So without going into too much detail, so if you, in this case, you will have 6 curve P because there's only 1 facility there, its weight is 6, that's the 6, plus 1 curve Q is at most 6. Again, if the weights were all 1, you will have curve P plus curve Q is at most K. So this is a generalization. And now, so again, in a generic instance, you could start with general instance, and you will end up with these 2 inequalities. And you want to solve, what is the question that you want to solve? You want to open facilities whose total weight is at most 6, that's right hand side, the second inequality, and profit is at most 11, at least 11. So that is actually enough. So again, the rounding algorithm, you can come to this situation where I have 6 curve P, in general, 6 of a linear combination of the curves is at least 11, and another linear combination is at most 6, and I want to pick integrally, so that the total budget is at most k and the total profit is at least m. That's precisely a knapsack problem. And in fact, so as Rishi said, there's a pretest to solve this problem. But in fact, we don't even need a pretest. So can someone say why this knapsack problem is actually solvable?
Counting, it counts the
Not the curves. The number 6 there is the number of children. The number of children is between 1 and n. So the numbers are small. So it's a knapsack problem with small numbers. So just a dynamic program will solve it exactly. So once again, I have an instance. I write the same LP. I have my curves. I run the same algorithm. I end up with a knapsack problem. And if all goes well, this knapsack problem has a good solution. But as this example shows that this knapsack problem just does not have any good solutions. If it did, I will be happy. But it doesn't. There are instances where it doesn't. It's not a surprise. Then the guy character. So the rounding failed. And the round or cut approach says when that happens, what is it? It means that these curves are cheating curves. They are cheating the solution. So in particular, there must be some inequality that all good solutions, all integral solutions satisfy, but this one does not satisfy. And if you can find that, in this case, in this example, this is such a valid inequality. Valid inequality is an inequality that all integrals satisfy, but this one doesn't satisfy. If I can find that, I'll add it, solve the LP again, try to round it again. And anytime the rounding algorithm succeeds, I'm happy. But I'm hoping that when it does not succeed, I can find this value inequality. The question is that, is there a principal way of approaching this? Because is this sort of clear? So more generally, I have a problem for which I have a rounding algorithm. Maybe I found that rounding algorithm by solving a simpler case. I take the same algorithm and I try to run it. And if it runs and rounds and gives me the 3 approximation, whatever approximation I'm choosing for, great. If not, if there is a way to then say that this cheating, this thing that the LP gave me is actually cheating so much that there is actually an inequality which takes it out from the integer term, takes it out, separates it from the correct set of solutions from this solution, then I can add that and solve it. So this is a very generic, very old technique from OR literature.
This specific.
That's the question here. Is there a principal way of getting this? That's what we were going to ask. Same question.
So the second equation, the weights are not bounded.
Yes, they are not. The profits are bounded.
But even still, there is a DP.
Yeah, DP. If any one of them is bounded, there is. Yeah.
Why should there only be one inequality? Why can it not split the polytope into
You mean
validity among some variables?
why can there be only one valid inequality?
Why should there be one valid inequality?
No. There can be a gazillion of valid inequalities, but as long as you find one,
I'm saying why should there be one? Why can it not split the polytope?
it is not clear. So but that's a hope. So we're going to come to that. Why? That's the same kind of why or how will you find it? These are all great questions. So we'll come to that. Other questions? Okay. That's this technique. Okay. So the way I like to think about it is, what are all the valid inequalities? Okay. So to get to this question, again, remember the rounding algorithm only needed curves. There were no accepts needed, right? So I have curves and I have an algorithm for that. And it sometimes succeeds and sometimes it says sorry. So I have these variables. So what all inequalities can I add? So we added some natural ones, summation, ball one, etc. But what are all things? Well, where do these curves come from? Well, these curves come from linear combinations of integer solutions. What do I mean? So let's take a solution. So this is a solution, right? So imagine that the total weight of these two orange things is at most k. So this is a solution that is a valid solution. And once you open these, you precisely know which clients it covers. So for this solution, the curves on these dark blue balls is 1, and the curves on these other light balls is 0. But you can have another solution like that. And if you open that solution, the curves on those blues are 1, and these are also 0. And then you can take a convex combination of these solutions. So you can take half of that solution and half of this solution. And this leads to more interesting curves. Well, whichever, there's only one facility, one client here which is never covered, not covered in either solution. So its coverage is half of 0 plus half of 0, that's 0. And there's one client somewhere, I think in the middle, which is covered in both the solutions. So its coverage in the combination is half times 1 plus half times 1. And otherwise, everyone else is half. Okay? And you could take some other combination and you can get some other curves. So all these curves, which are obtained by convex combinations of integer solutions, they lie in the integer hull. Okay? They are my good curves. You cannot hope to separate them. They are not separable. They are inside them. So can I write all these curves? The valid curves arise from the combination of all such solutions. And you can see, it looks like a very gnarly polytope. In fact, what does it look like? It looks like this. Imagine a variable. Now there are exponentially many variables. A variable for every feasible solution. What is a feasible solution? A solution whose knapsack weight is at most k. And once you have that feasible solution, so I have a variable for this, and I open one of these. So summation gs is 1. And once you open that set, then curve v is 1 if the set is within distance r from that set. There is someone in that set which is within distance r, or is 0. And curve v is a convex combination of these things. So let me repeat this. I didn't say it well. A valid curve v, which is a good curve v, is a curve v that arises from this huge exponential size LP, where I have a variable for every feasible solution, and the coverage of a vertex v is going over all feasible solutions which covers it and adding up their problems. So it's a projection. Set of this picture on the right, the cartoon is for a projection of an exponential variable, exponentially mean constraint LP onto these covers. So it's ugly. We have no way to describe it. It's an integer hull. It's a NP hard object in some sense. How do I get valid inequalities? The answer. Oh, okay. So sorry. So the best LP relaxation. Before I go to inequality, the best LP relaxation is basically curve V's have total at least m inliers, and they arise from this projection of this Marley set. I cannot solve this. It's impossible to solve this. Just for a thought exercise at this point. But I do know that if this LP has no feasible solution, then my guess is this slide may be missing. So okay. So let me say it again. So this is an LP which has lots of constraints because the projection of exponentially and maybe exponentially constraints. I do know if this is empty, then my guess is too small. So there is an algorithm out there which tells me, even if I have lots of constraints, whether a polygon is empty or not, it's an ellipsoid algorithm. And what is the ellipsoid algorithm? Well, it says, even if these has exponentially many constraints, if you have this following ability, that given a point P, if you could separate, you could either say it is in this object, or you can separate it from this polygon by a separating hyperplane. If you had that ability, or rather more precisely, given a curve V, if you can find a separating hyperplane, this algorithm finds you a different curve prime V. And okay, that's not that hard. I can always find a new curve V. But the idea is that if you keep asking this with this new curve, whether I am in this polytope or a separating hyperplane, if you do this for polynomial in dimension many times, either you'll find something in it, or you'll prove that this is empty. And empty in this case means my guess is too small. But there is an algorithm out there. But I would like to stress again that the LP that we wrote, we cannot hope to have a separating hyperplane because if we could do that, then we'll solve the problem exactly. The round or cut paradigm is the following. So I'm going to start with some curves. How? Which curves? Maybe the curves that I began with the small LP. I'm going to run my rounding algorithm for k-center, robust k-center, this LP guide Hopf noise. As I tried to say, I'll end up with a knapsack problem. If I solve the knapsack problem and I get total profit of at least m, yippee-yi-yay, I'm done, I got a 3 approximation. But if I don't, and this is the part which both of you are asked, I get a separating hyperplane. It's not clear. But if I could do this, then I can run it to ellipsoid. Ellipsoid will give me a new curve prime V, and I'll repeat. So this part is not clear. But suppose I could do this. What does this imply? It implies that in polynomial times the approximation. Why? So imagine that anytime you escape this yes path, you got a 3 approximation. You got something. So imagine you never did this. I mean, you can assume you never did this. What does that mean? It means that there is this gnarly object, and every time this part, this no part, gave me a separating hyperplane. As far as ellipsoid is concerned, it does not care where the separating hyperplane came from. If you gave me separating hyperplanes, I'll give you a new cuff prime, cuff double prime, cuff triple prime. And I know that in polynomial many rounds, if you keep giving me separating hyperplane, I will tell you that this thing is empty. And if you tell me this thing is empty, the guess is too small. So the idea is, how do I get this? Is this clear? So this is the round reflect paradigm, and it's not special to clustering problems. It doesn't apply from many things. I'd like to stress the difference is that I'm not asking ellipsoid to separate every curves. I'm only asking to separate some curves where the algorithm fails. That's the new thing. So where do I get this from? This is a slide. So this is a gnarly object. It's a projection of this exponentially sized object. So what this implies, if you write the dual of this, and I'm going to spare you the process of writing the dual, but it's a mechanical dual, but it leads to all the value inequalities on these curves. How do they look like? They look like the following. Lambda v's here are coefficients. Think of lambda v's as coefficients. So if you find lambda v's which satisfy the following, if you take any feasible solution, S is in F with weight at most scale, and I sum up the lambda v's of all the clients covered by the solution, if that number is less than n. So lambda v's are real numbers, they could be negative as well, they're real numbers with the property that any feasible solution, if I look at the lambda weight of the clients covered by them, that is strictly less than n. Then I can assert that this is a feasible valid inequality. Okay. In particular, if lambda v's were 1 and it satisfied this, then it means that this LP has no solution. So sorry, this instance has no solution because any solution you pick, the total number of clients is covered is strictly less than n. And so this will say summation cup B is strictly less than n, which will violate the summation cup B is at least m, and then I think will be m. What this is saying that I don't need lambda v's to be all ones. If you find any real numbers which has that property, this is a value. But this is a hard thing. It's an infinite set. But this is just it's a what is it called? It's a syntactic thing right now. How does it connect to the rounding algorithm?
Why is this strict inequality?
Why is the strict inequality?
They're showing up because
it does not show up. It's just for this convenience. It will be a non-strict with m minus epsilon. This is the same thing here. Again, this is just something to keep in mind. Where were we? We rounded, we got a knapsack problem, but we were unhappy because the total profit was at most. So it's something like this. So that resulting knapsack problem was looking like this. And I had 6 cups P plus 6 cups Q is at least 11, but 6 cups P plus 6 cups Q is at most 6 or something like that. And I had a knapsack solution which failed. But when I have a knapsack solution which is failed, then I can use that knapsack solution to get these lambda v's. In fact, lambda v's will be precisely the number of children. So you are asking where is the 6 cup P plus 6 cup Q? They were the lambda v's, which were the number of children that these representatives cover. Why would these lambda v's satisfy the top thing? Well, that's because the knapsack problem failed. If there was a knapsack solution where the summation lambda v was at least m, since I can solve knapsack exactly for these small weights, I would have found it, but I failed to find it. So it must mean that these lambda v's with the children satisfy the top premise, which means that this is a valid inequality, and that's the one that we added. That leads to P approximation. So this is unarguably fast, right? But the idea is that you try to round, right? And maybe the mantra, maybe the recipe is this, right? You come up, you imagine, so you have a rounding algorithm. You imagine that your solution that the LP is giving you comes from the integer hub. And you design, so this is the designing rounding algorithm, and then you understand when it fails, right? In this case, it failed because the knapsack was leading to a smaller thing. And if you can then say that the reason it failed, okay, the reason it failed is a linear reason in some sense. I can write a linear inequality, I can derive a linear inequality out of it which separates it. Then the round of cut will work. Okay. So if the condition fails, then argue that the LP solution was not in the hub. That's the generic technique. So you come up with a rounding algorithm, and maybe the takeaway is that don't get too afraid if you get an inequality gap. As long as you can prove that if it were in the correct integer hull, my rounding algorithm will work, there's a high chance that the round of cut technique. Of course, it needs this fact that if it came from the LP hull, your rounding algorithm could be bad. So there's creativity still required for that. But if that is the case, then this technique is something to keep in mind. And this is something that has been used in other clustering problems. And why clustering? Because again, clustering, initial clustering problems where there are constraints like cardinality constraints or coverage constraints, which are like simple, like the number of outliers. They were simple enough for the LPs, the normal LPs to be good. But when you have weights or something more like more generic coverage constraints which arise from fairness, etc., then you start, the LPs, normal LPs are, you can easily find inequality gaps. And these were some examples where this technique has had some recent success. I'm not going to go over this. I'm happy to talk offline about some of them. But that's maybe the take-home point. And I'm 5 minutes over time, so thank you for your attention.
This example that we gave, the dual has exponentially many constraints. So you need a separation oracle for that.
No, so again, both these things are unsolvable because they are like if you could solve these things, you'll be solving an NP hard problem. All you need is when your rounding algorithm fails.
That gives you a separation.
Correct. Yeah. So it's not at all possible to solve this separately. So again, so this idea of taking the dual is nothing to do with clustering. It's a very generic thing. We do it for any problem at hand. The creativity again is that there was a rounding algorithm from which you could use to find a valid inequality. That changes from problem to problem.
Why is this valid inequality valid?
Why is this violated inequality? Sorry,
This has to be violated by the cup.
Correct. Oh, so in this example, this was the 6 cup B plus 6 cup Q is at least 11, which was what we derived from the rounding algorithm.
So that's the construction of the knapsack.
That's the construction of the knapsack, and that is the inequality, the reverse of it.
Do you have any further questions? We can try this thing.
Thank you.
Open it for appreciation.
Oh, wow. Thank you very much.